Welcome to the first video to help you get through this course of statistics. I want to assure you that pretty much everything that you'll be doing is very much like the math that you do on a day-to-day basis. Simple addition, simple subtraction, multiplication and division, and in fact the most complicated thing that we're going to be starting with and that will become a part of what we're doing on a regular basis will be calculating average. I'm going to start talking about it on a very conceptual level that you would deal with on an everyday basis, but then we will end up converting this into the language and notation of statistics, and once you tie what you already know with the new bits, that language of statistics, you'll find that it's very straightforward and easy to follow along. So we're going to use a simple example early on in the video series to help you get locked into the statistical notation with this just simple concept. So imagine a situation where you left your window to your house open, several flies managed to get in, you're deciding what to do with them, you think that you're going to shoo them out of the house, but as you're trying to do that, you notice that they're all a bit different in size, and more importantly, you notice that their wing lengths are slightly different in size. So instead of just shooing them out, you decide that you're a bit curious and you start to measure the lengths of their wings. That's what you actually want to do. So you start to capture them all and you measure the lengths of their wings, and you notice that some have very short wings, some have very long wings, and so you just want to get an understanding of this particular group of flies. And since all you're going to be doing is dealing with this one group of flies and describing them, these will be known as descriptive statistics, at least initially. I do realize that some of you might be budding scientists and you might think to yourself, well, there's reasons why some of them might have short wings and some of them have long wings, but we're going to deal with that later. We want to keep this as a very simplified example. So understand or imagine in this case that basically they're all the same age, they're all of the same species, and they've all had similar access to food and such. So just as you would in real life, you capture 25 flies, you measure the length of all of their wings, and you basically just organize that data. In this case, we've just put it in simple from smallest to largest. And then to calculate an average, just as you would in regular life, you're just going to add up those values. In this case, we get 112.5. You would divide by the total number of observations that you have, which is 25. That's going to give you this average of 4.5 millimeters. That's the average length of the wings of this particular group of flies is 4.5 millimeters. So that's a simple thing that we've done a number of times in our lives. We just now have to convert that into statistical notation and how we deal with that in statistics. So in statistics, we take exactly the same values that we had before, but now we're going to basically give it an indicator. In this case, X will be the X is the marker to indicate that particular distribution, because later as we get more groups we might have X1, X2, X3, and X4 as we refer to multiple groups, or we might have an X group and a Y group. So all it is a placeholder saying I am discussing this particular group. So what did we do before? We just took those values, we added them up. We're going to do the same thing, but we have to add statistics speak to this, or the language of statistics. So average in statistical notation will be identified with the Greek letter mu, and so that will be what we will call the average for this group is mu, and then we have to sum the values. So in statistical notation we use the Greek uppercase sigma, and that indicates sum of. So we're going to, literally what this reads is, to get the average, you will sum the X values and then divide by the total number of observations. So we do exactly the same thing that we did before, is we're going to sum those to get 112.5. We will divide by the total number of observations, in this case 25, and again that will give us an average of 4.5, but instead of calling it average, we will call it mu equals 4.5. So we have to also look at how statisticians think about numbers. Since we've captured every single fly and are only interested in these particular 25 flies, we can consider them a population. As we're only going to use the values to describe these particular flies, we will be creating what's known as descriptive statistics. However, if we were going to use these flies to make assumptions about flies in general, then at that point we would be doing inferential statistics, because our sample would be used to make inferences about other groups of flies. If we were to do that, the 25 flies, meaning if we were to do inferential statistics, the 25 flies that we have would no longer be a population, but it would now be a sample, because we would be inferring about larger groups or other populations. But there will be more on that later. And as we look at this, although this is a hypothetical data set, we often find that even when plotting real data, it falls into a normal distribution, sometimes known as a bell curve. That natural tendency forms the bulk of statistical theory and is how hypotheses are mathematically evaluated in this class. So as you look at this distribution, all I have done is taken the values for the lengths of the wings of all the flies that I've calculated and then plotted them on a number line so that we see that the most common observation is 4.5 millimeters, and then we plot 4.4, 4.3, and 4.6, and 4.7, and so on. And we have fewer of the very small wing lengths and fewer of the very long wing lengths. But as you notice that some have small wings and some have large wings, you may think to yourself, well, those are abnormally large or those are abnormally small. But then the question in statistics is, what defines abnormal? When is abnormal actually abnormal? And so that when is it not average is an important concept in psychology and psychological statistics. And in psychological statistics, we generally consider that value to be alpha of 0.05. Don't panic, I'm going to talk about what exactly alpha of 0.05 means. What abnormal means statistically is it's unexpected. It's not part of the norm. So if we look at a distribution again, in statistics what we do is we take 5%, so if we have all of the observations, that forms the entire bell curve, then that would be 100% of the observations. But alpha equals 5%, really what that means is we are saying the 5% most extreme values are not average or unexpected. But since we have 5% and we have to divide that into the two tails, the most extreme and the least extreme, that 5% is going to end up becoming 2.5% in each side. So what defines normal in psychology? The middle 95%. What defines abnormal? That would be the most extreme 2.5% on each side. When you add those together, that's 5%. That's what it means to have an alpha of 0.05. So we're going to learn next how we calculate what numbers fall into those tails and the area in those tails, but we're going to do so in a way that doesn't resort to calculus. I do want to point out that not everything is normally distributed. There are other types of distribution. One type of distribution is a skewed distribution, but we also have different things called kurtosis. We're not going to worry about those very much in this class at all. So just most of the assumptions that we make will be based on a normal distribution. So we're going to start with a center point as we have. We've already calculated mu equals 4.5. But then when we look at our distributions, if you look at the data, we have and use an obvious approach and go with equal distances, then with an average of 4.5, we could go minus 0.2 on one side, resulting in 4.3. So again, we have to deal with this distribution in one way or another. In this instance, I'm looking at equal steps. So if I go minus 0.2 on this side, that's an equal step, and then the next step would be minus 0.2 over here. Or if I go to the other side, I'm going plus 0.2, plus 0.2, so my step is 0.2 each time when I look at the number line. But if I go with equal steps, then what happens is the area under the curve ends up becoming different. So I have 0.2 for the step here, but it's 34.13% in terms of area. 0.2 for the step here, but it's only 13.59% in terms of the area here. So if I have equal steps, I end up with unequal area. My other option would be to go with equal area, as we see over here. So if you'll notice, I have 16.6% area under the curve, but because this part of the curve is taller, then what happens is that's a skinnier amount in terms of the actual step. My next step, this is also 16.6% in terms of area under the curve, but in order to get that first 16.6%, my actual step is only 0.09%. Whereas if I want to do that next step to get the next 16.6%. That's actually 0.1 for the next step. And then if I even look at that next step to get the 16.6%, then that next step is actually much, much more. We go from 4.69 to 5.65. So if I'm dealing, and that's actually going to be 0.96 in terms of that next step. So I either have equal steps but unequal area, or I have equal area, but that results in unequal steps. So in psychological statistics, we opt to use equal steps with unequal area. But the numbers we've used only works for the fly wing data set. An average of 4.5 millimeters can't be directly compared to, say, the average length of a giraffe's neck. Or if you want to talk about it in common parlance, I can't compare apples to oranges, but I can convert them both to a common mathematical language. So sometimes we'll need to deal with the actual data set, and sometimes we'll need to deal with the common mathematical language. We start with the statistical assumption of a normal distribution, which can be tested if necessary, but we won't be doing that. We'll start with a center point, that is the average, and then we want to establish standard steps. Even though the average is the most common observation because it is the center line and the highest point in the distribution, there are still many more observations that fall off of the center line. So let's take a moment and reiterate what I just said there. At 4.5 millimeters, the most common observation for a fly's length is going to be 4.5. What I mean by most common, though, is just of that one measure. If we look at that, that's just one line. We've got the whole rest of the distribution on the plus and minus side. So there's actually going to be many, many more flies that have bigger than 4.5 millimeter wing length, and many, many more that actually have smaller than 4.5 millimeter wing length. So we know that some flies are going to have exactly 4.5 millimeters, but instead of that, it's going to be 4.5 plus or minus some degree of variation. That's the more common observation. And we can calculate what that degree of deviance from the average is, or what that degree of difference, and we call that the standard deviation. So first we're going to calculate that for our actual data set. Then we will convert that to that standard mathematical language that I was talking about that converts every average into a standard average. So it doesn't matter if it's fly's wings lengths in millimeters or a giraffe's neck in feet. After we convert the average into the common language, then that average score instead of 4.5 millimeters will always be 0, and the standard deviation will always be 1. Conveniently, when we do this, it turns out that if we convert to this standard, so we convert to the standard mathematical language instead of 4.5, we have that average of 0. One step above would be plus 1, one step below would be minus 1. If we look at plus 2 steps, then what we find is the area under the curve in that very, very end tail is very, very close to that magical 2.5, or 2.5 on both sides gives us 5%. So that standard mathematical language is going to be very closely associated with that alpha of 0.05 that we talked about. So this may be a little bit confusing, so again, let me just highlight. If we have equal steps, we have unequal area. If we have equal area under the curve, we have unequal steps. Statistics chooses equal steps but unequal area. We can then use that data set, we can convert it to a common language. If we do convert it to a common language, then when we go 2 steps above, the area in that tail is very close to 2.5%. In 2 tails, you add the 2.5% together, you have 5%, or that not expected by chance or basically abnormal range. So it will take us a couple of steps to convert any data set into that standard 1-unit steps. But the first step is to calculate what is conceptually an average distance of each score from the mean. So let's go back to our data that we had. These are all of our houseflies. We've calculated that average, mu equals 4.5, but some of them, for example, this housefly, only has a wing length of 4.2 millimeters. So if we look at that value up here, 4.2 minus 4.5, its distance is 0.3 millimeters away from the average. So it's negative 0.3 millimeters away. Another fly that we caught had 4.9 millimeters. So if we look at that and we do the math on that, we have 4.9 minus 4.5, or 0.4 millimeters away. So if we look at this list of numbers, negative 0.4, negative 0.3, negative 0.2, etc., these are all the distances away of the flies with the shorter wing lengths. These are the distances away from the mean of the flies with the longer wing lengths. So just as we calculated an average wing length, we added the numbers up and divided by the total. Conceptually, we want to do the same thing with these values. But if you've been paying attention, when we add these up, we're going to have a problem. Because in this case, if we add them up, we end up getting the value of 0. But we know that that can't be right because there's distance on both sides. So what happened? 4.2 minus 4.5 gives us a negative number, whereas 4.5 minus 4.7 gives us a positive number. So we have some values that end up being negative and some values that end up being positive. So how do you end up fixing that? Well, one way would be to take the absolute value of all of these. So I've got negative 4 as we look at this value here, but that's still an actual distance of 4. We could just take the absolute value of that, and that way you wouldn't get 0. Unfortunately, in statistics we don't do, I don't know that it's unfortunate, but basically we end up not taking the absolute value. We actually opt to square those values instead. So what happens is 4.1 minus 4.5 gives us negative 4. But if we take negative 4 and square it, multiply by itself, negative 4 times negative 4, then at that point we end up getting rid of the negative, we get 0.16. So by squaring all of these values, we get rid of the negative signs, and so now if we square then sum, the total will never be 0. In this case, when we finally square them and we add them all up, we actually get the value of 1.0. So we get rid of the problem of adding to 0 that we had before. In statistical notation, how does that look? We have that sigma symbol again. Remember the Greek sigma, capital sigma, that means sum up. But remember, your order of operations, you need to do what's in the parentheses first. So what this is asking me to do is take every x value, the actual fly that I measured. So in this case, I took this fly with 4.1, and I subtracted from that the mu, the average score that I got. So 4.1 minus 4.5, and then it's going to be, after the parentheticals, the next order of operations would be to square it. So that's going to be 0.4 squared gives me 0.16. And then after I do that for all of the x values, then my final step is to sum them up. So what this is inside of the parentheses, do all of your subtraction. Then the next order of operation would be do your exponent for all of them. Then finally do your summation and add them up. That gives us a value of 1.0. Remember, as we go back to the average that we just computed, how do you compute an average? You sum the values, then you divide by the total number of observations. That's what we did before. We summed and divided by the total number of observations. We are wanting to calculate an average distance. So what have I done? In this case, I have summed the values. That leaves us with a division that we still need to do. So I've summed the values, but what I've actually done is I've summed the squared differences. So in statistics, we actually call this sum of squares, or in shorthand, just SS. I want to emphasize to you, sum of squares is not that difficult. You're just subtracting, then squaring, then summing. But this is one of those operations you will be doing over and over and over in the class. So any time that you see this formula, in your head you should immediately be thinking sum of squares, or SS. Those two things should be inherently linked together, and anytime you see that formula, you should practice computing sum of squares because you want to be very good at and efficient at doing that, because it will come up a lot and it is the foundation of almost all of the statistics that we'll be doing. So if you get good at calculating sum of squares, you've already taken care of one of the hardest things that you'll have to deal with in statistics. So we've done the summing, but to calculate the average, we need to divide by the number of observations. We haven't done that yet. So again, our formula that we're looking at for an average is we've got the sum on the top. We need to divide by the total number of observations. In other words, remember when you see that formula, you should immediately think to yourself, SS, sum of squares, divide by n. In this case, we have 1.0 that we're going to divide by 25. When we do that, we get 0.04, but remember we squared them early on, so in order to offset that, we're going to have to take the square root. So when we do that, we take the square root of 0.04, we end up getting 0.2. So the standard deviation in this case will be 0.2, and that is referred to with the Greek letter lowercase sigma. So I will still be using sigma, but this is the lowercase. So our standard deviation for this group of flies is sigma equals 0.2. What does that mean? When we catch a fly, we expect it to be 4.5, but not exactly 4.5. We expect it to be 4.5 plus or minus some amount. Well, that amount is 0.2 is what it turns out to be. So anytime we catch a fly, we've got a great deal of expectation that it will be 4.5 plus or minus 0.2. If we think about that, that's going to range from 4.3 to 4.7. So if we were to turn this into a story problem, it might read something like the following. A researcher who is interested in the common housefly wants to know just how much size difference there are between the wings. So he catches all of the 25 houseflies from his house and measures the wing length in millimeters. All of their wings range from 4.1 millimeters to 4.9 millimeters. To start with, he wants to know the average wing length. So he goes to the statistics books and the formula says sigma x divided by n. What I'm doing here is I'm reiterating what we just did, but I'm now providing you with the basic steps to follow for all statistics, and it will help you calculate them without making errors later on. So what I highly encourage you to do, and has been very beneficial for my students, is if you want to be cautious and not make mistakes, create a toolbox. Take the formula, break it down into its individual components, and put those in the toolbox. I know to calculate the average, I'm going to need to get sigma x. What is sigma x? Blank. I know I'm going to need to get n. What is n? Blank. Okay, so it's very simple here. It seems overly simplistic and overly basic, but later those toolboxes are going to get quite large, and if you get into the habit of following those steps, filling in your toolbox, then you're not going to get lost in the numbers and values that you have. So after calculating sigma x, that value will go there. After calculating n, it's going to go there. We've already done this. We know that we're going to end up with, and I encourage you to just go ahead and do this on your own, actually calculate this through. I've left sigma x on there for you so you can put it in 25, then put those into the actual formula. Sigma x is 112.5 divided by 25, ends up giving you 4.5 again. But now the researcher wants to calculate the standard deviation because he wants to know on average what is the distance each fly's wing length would be from that average of 4.5. So 4.5 millimeters is the average length, but the average distance away is the standard deviation. So as we go to that formula, again, that formula overall is the standard deviation, lowercase sigma, is equal to the square root of the sum of squares divided by capital N. Again, when you see this, you should be thinking immediately sum of squares. You'll create your toolbox just as we did before, which asks for sum of squares and n. So what I'm doing is I'm providing you with the data that we had before, but now I'm giving you blanks. I encourage you to go ahead and fill this in and practice doing the sum of squares because, as I said, that's one of the most fundamental and foundational statistics that you'll have to do. So what am I looking at when I'm looking at these values? 4.1. That is the actual fly's wing length, and then 4.5 is the average that I calculated. So the formula again is asking me to do what? Take the actual value, subtract it from the average, then square it, and then after I've subtracted and squared them all, then I will sum all of those values. So try to calculate this without looking at the slide where we had just done that value. So after subtracting and squaring, I sum them all up. That's the sum of squares, sum of squared deviations. And then after I've done that, the number of observations I need to divide by that. The question is, has it been provided or does it need to be computed? So to compute it, all I'm doing is counting the number of flies that I actually captured. Once I've done that, then what I do is take that square root, and that gives me the standard deviation. So in this first video, what you've been introduced to is some of the notations for statistics, the language of statistics, and the basic steps of statistics. As long as you follow on, build your toolbox, because again, those toolboxes are going to get bigger, and follow the steps in order, the computations aren't that hard. I'm not asking much of you here. I'm asking you to subtract 4.1 minus 4.5. That's not a difficult subtraction. Once you end up with negative 0.4, I'm just asking you to take negative 0.4 squared, or times itself, negative 0.4 times negative 0.4. Again, that's simple multiplication. It's not a difficult thing. Once you've done that squaring, then you're just going to add all those values. Again, all I'm doing is subtracting, adding, squaring, dividing, things like that. It's all very basic and straightforward. But in this first video, that is the foundation. It's the basis for most of the statistics that we're going to do for the rest of the semester. So I encourage you to practice this. Look at the ones that are also in your textbook. Maybe get online and do a Google search for sum of squares practice or standard deviation practice, or just make up a data set and follow the steps. As long as you follow the steps, even though you don't have the answer provided for you, if you carefully follow the steps, you'll be able to get that answer correctly without any concerns, and that will put you in good shape for the rest of the semester. Thank you for watching video 1, and soon I will encourage you to go to video 2 and start learning more about statistics.